Okay, so some brief announcements. We've settled on some recitation times. Um, whoa. And these are a little bit odd times, but it really had the largest overlap with everybody. And the way we'll do it is so you remember which day it is a little bit easier on the weeks that homework is due. Uh, we'll have a recitation just the day before on Wednesday. And that'll be a late one, 7 to 8 p.m. It's like for desperate people who might have to pull an all-nighter to finish it or something like that. We'll have a recitation from 7 to 8 for that. If homework is not due on that week, then we'll have a Thursday time. Of course, they're all recorded, but these are actually the times with the most availability for people for whatever reason. So I think only 3 people said they couldn't make each date, and then there was no overlap. So everyone should be able to make at least one of those. Yeah. So, and the other thing was do the quiz. Hopefully it's working. Yeah. Any questions about that? Homework's not quite due yet, but definitely start looking at it. You should be able to do all the problems that have to do with solving the Schrodinger equation. There's also an NMR question, which you can basically start looking at, and yeah, and there's a variational method, and you should basically be able to do all the homework after today. So it should be plenty of time to do it. Okay, any questions about that? So do quiz, do homework. Yeah. So I had a interesting question about the model we were looking at for bonding and so on. I wanted to emphasize again what's this model about. Again, the basic idea is you have some atomic centers, and you're just looking at what a single electron, what its energy would be if it's in the presence of these atomic centers. And the idea is that, well, one option is if the atomic centers are completely disconnected from each other, right? Then if all these are like carbons or something, then the electron can sit either here, here, or here. It'll just be bound to one of those atoms, and it'll have some associated energy, E0, right? And it'll be a triply degenerate energy level because, of course, there's the 3 carbon centers, and it can sit in one of those 3. And so, you'd have this is how we formed our basis, the electron can sit in one of those 3 places. But the idea is that those are not the energy eigenstates, right? The idea is that the electron, if it sits in one of these centers, it feels the presence of the other nearby centers. So there's some nearest neighbor interaction, right? And if you have like a linear chain like this, this guy sits next to this guy. There's some kind of interaction between the atomic centers that will that will form a bond. And maybe that interaction is already induced by the existing bonds that are already there, by the electrons that have already been placed. But we're just thinking about a single electron and what happens if we try to place it into the system where there's an interaction between neighboring atoms. And we don't know what that interaction is exactly. We don't know what the energy of it is precisely. It's hard to model. So we just say that there is some probability, right, due to that interaction for the electron to transition from one carbon center to another. And so that's the entire model, and associated with it is going to be some term in your Hamiltonian, which is a matrix that's 3 by 3. That there'll just be some off-diagonal term that corresponds to transitions, and it's the only thing that the off-diagonal terms ever correspond to. It's either the diagonals, which would be the bound states if there were no interactions between neighboring centers, and otherwise, it's going to be the off-diagonal terms will correspond to the transitions between nearest neighbors. So on the diagonal, you just have the bound state energies, and if there were no interactions, no bonds or anything, then the Hamiltonian would just be this, right, with a bunch of zeros. But it's not. There's going to be some interactions. The first carbon will interact with the second one, so there's an off-diagonal term here, and of course it's symmetric. And the second one will interact with both the first and the third, so there's some minus a's here, and then this one, of course, the third interacts with the second. So that's what the Hamiltonian actually looks like when there's some interactions. And we assume that this hopping term, it can only correspond to hopping because this is the term that gives you a transition between state 1 and state 2, right? This is the sort of psi 2 psi 1 matrix element, where these are the the basis states, the bound states. And so this is what the Hamiltonian looks like for a chain. And so then if you're asking what energy will a single electron have if you place it in the system, that will be the smallest eigenvalue of this matrix. And that's what we were doing. We're just finding the eigenvalues and eigenvectors of H, and then saying, well, the electron, if you place an electron here, it'll go to the lowest energy, right? And that's the smallest eigenvalue of H. But then the problem is that in a molecule, you have to place multiple electrons, not just one, but however many you have. And each time you place one, you start filling up. So these are maybe your energy levels. Each time you place one, you can only place 2 electrons in a single energy level, right? If it's a non-degenerate one. So because of the Pauli exclusion principle, which we'll study later on, but again, you can only place 1 and then 2, and they come in with opposite spins. And so as you place more and more electrons, you start filling up higher and higher eigenvalues of this matrix. And so then you just count. So there's 2 that go in the lowest one. And then as you fill up more electrons, the third one will have to go to the next highest, the one above the ground state, and so on. Of course, you also have to count degeneracies. Sometimes you have multiple energy levels at the same level. So then, more electrons can go here. But it's only 2 per state because an electron also has a spin, so it can be spin up down. And Pauli exclusion says that fermions can't have exactly the same quantum state. So they either have to have different spins or they have to be on different energy levels, because those are the only quantum numbers we have. We have its energy and then its spin. That's it. So that's the idea. I wanted to emphasize that again, maybe state the model in a different way, just to make sure we get that. So that was what we were doing. But now we're going to go back to NMR. So any questions about that? So just as a little bit of a review for the bonding model. It's a nice model for those of you interested in mathematics. Essentially, the matrix you get for the Hamiltonian is the adjacency matrix of the graph that you have of the centers and their bonds. So if you know about graph theory, it's maybe of interest to you, so you can start thinking about the eigenvalues and eigenvectors of adjacency graphs of adjacency matrices of various graphs. It's kind of fun to think about. If you have an arbitrary graph, what's the smallest eigenvalue of its adjacency matrix? An adjacency matrix is just something that says if you have a link between two nodes, then the corresponding matrix element that links these two nodes, this kind of thing. If this is node I and this is node J, then Aij, the adjacency matrix, is 1. If there is no link, then it's 0. And the fact that there's stuff on diagonal just kind of means that there's a sort of link connecting each node to itself in a sense. So yeah, so the Hamiltonian is basically a diagonal matrix plus an adjacency graph for the links times minus A. All right. And then I told you, we calculated how you can get minus A from an experiment, from a chemical reaction. You can actually just measure what it is. You don't have to know the details of, the electronic structure of the carbon or the atomic centers or anything. You could just measure it by breaking the bonds in an experiment, right? And then it's the energy of those bonds that that is responsible for, that A contributes to. So you can extract A. That's what we did for benzene. So yeah. But yeah, so now we're gonna go back to NMR. Here, I left this stuff over from last time just to review. So again, what are we doing with NMR? We're looking at a spin 1/2 particle, and it's pointing in some direction, and we're having a static field applied in the z direction. That's the B naught, and then we're applying an oscillating field in the xy plane, perpendicular plane. It's sort of spinning around with some frequency, an applied frequency. So we know that in a static field, the spin will precess around that applied static field with a characteristic frequency that has to do with the gyromagnetic ratio and so on, the magnitude of the B field. But it's got some precession frequency. That's the Larmor frequency. Then we apply this oscillating field, some applied frequency omega, and then because of the coupling to that oscillating magnetic field and its magnitude, there's an associated Larmor-like frequency for that field also, and that we call the Rabi frequency. It's just some names for there's three different frequencies, so you have to call them something. This one's called the Rabi frequency, and what happens is you can actually solve the Schrodinger equation, the time-dependent Schrodinger equation, in the presence of the oscillating field and the static field. And we saw that you get these two differential equations for the coefficients of your state. It's just a qubit, so it's just a two-dimensional Hilbert space, easy. And we saw that it's nice to move to a rotating frame, which in the context of these coefficients just means you look at this variable change, where you multiply your coefficients of your state by e to the plus or minus the Larmor frequency. So you're trying to be in the co-moving frame of the precession frequency, right? It's precessing around the static field. If you move to a co-moving frame, then you're in a frame which the spin looks stationary, even though it's precessing around z. And if it's stationary and you're on resonance, your applied frequency is the same frequency as the Larmor precession, then in that rotating frame, what it looks like, it looks as if you just have a static spin in an applied field in the x direction, because the whole thing will just be rotating around z coherently, right? It's on resonance, so it's rotating with the same Larmor frequency. We made the applied frequency match the Larmor frequency. This is the applied frequency. We made it match this frequency. And so what happens is you just get oscillations. Now you just get, it's as if you have a static field and you get precession around that applied field direction, which is rotating with your precession frequency. And so then you just get another precession, except in the perpendicular direction, in the direction of the co-rotating applied field. So you just get a precession along x in the rotating frame. And of course, what's the frequency of that precession in the orthogonal direction? Well, it has to be the Rabi frequency, because that's the characteristic frequency associated with the gyromagnetic ratio and the magnitude of the applied field, the delta B, the applied field. So yeah, and that's why we looked at this case where the applied field frequency is equal to the Larmor one, because then things are kind of simple. The solution is just a precession around the applied field direction, which is rotating with the Larmor frequency, because it's on resonance. And we saw that that's what you get, that you just get precession around the x direction. And so what would that mean? So that means if you start with a spin that's pointing up in the z direction, if it's precessing around x, right, it'll just flip from up to down, up to down, up to down. With what frequency? With just the frequency given by the Rabi frequency, the magnitude of the applied field. And that's it. So that's on resonance. What happens is if you start with spin up, you apply a perpendicular field that's on resonance with the Larmor frequency. Then it'll just precess around that orthogonal direction, which means it'll just rotate. Hopefully you see my pen, sort of, it'll rotate from up to down. And that's the kind of the most dramatic effect that you can get for this kind of oscillation. So, you know, this is, you can do this. This is a nice technique, right? It means that you can, if you know the Rabi frequency, you can sort of flip your spin at some predefined rate, and you can turn it in different directions just using this rotating applied field. So that's nice. And now the question is, what happens to these oscillations if you're off resonance a little bit? So let's do that. If you're off resonance, that's where we left off last time. But yeah, any questions on what we did so far? Okay, so if you're off resonance, well, then your differential equation for those coefficients changes a little bit. So you get 2 over omega 1 d squared gamma up over dt squared. You get a new term that's proportional to the detuning, as it's called, the difference between the applied frequency and the Larmor frequency. But then the other terms are sort of the same. So if, remember we got this equation, it just comes from taking another time derivative of this equation. And when we had resonance, this exponential term went away. But if it's still there, then there's an extra time dependence here. So when you take another derivative, what'll happen is you'll hit this exponential and it'll bring down a factor of I delta, plus or minus I delta. And if you only look at the up arrow guy, what will happen is, so on resonance, we just had the single term. But when you're off resonance, then you not only get this term, which is what we had, but you also get this middle term, the term due to detuning, just because that derivative has to hit that exponential too. So you'll get this term. But you can still solve this. This is a second order differential equation. I've showed it just for the up guy, but you can put minus signs and put the down coefficient as well. But it's still a second order, ordinary linear differential equation. So it still you can solve it using, the maybe you don't remember from your sort of undergrad differential equations class, but these equations are relatively easy to solve. You just look for solutions of the following form. You say, well, we expect to get oscillations, so we get an e to the I, but we might not know the frequency of those oscillations, so we put in an omega coefficient plus or minus. And those are the two fundamental solutions. The second order equation, it's going to have two fundamental solutions. If this term wasn't here, then we would just get plus or minus, right? E to the plus or minus I omega t. That's what we had before for just recall back here. We had this equation. The solutions are just these exponentials. But if you have an extra linear term, then you don't really know if it's going to be plus or minus. It's just going to be some coefficients, omega plus or minus. They don't necessarily have to be plus or minus some frequency. We'll just see what they are. Times t. So you take this solution, right? These two, and you plug it back into here. And once you plug that back into there, you will get an equation for the omega. And if you substitute that in there, what you'll find is that this equation becomes an equation for the omegas, and you'll find that omega plus or minus is equal to delta. You just get a quadratic equation. You take two derivatives with respect to time, right? That'll bring down two factors of omega. So you get an omega squared, right? This will bring down one factor of omega. And the i's will cancel. So you just get one factor of omega here, and here you get no factors of omega. So in the end, you'll get, what do you get? You get some coefficient a, well, we can write fine. We can write down what it is, right? So you take two derivatives with respect to time. This becomes minus 2 over omega 1. And it's plus or minus squared because you get two factors. Here you pull down one factor and the i's cancel. You get 2 over omega 1 delta omega plus minus, just one factor. And then over here you just get plus omega 1 over 2 and no factors, because there's no derivatives, and that's all equal to 0. The overall exponential just cancels. So, okay, this is a quadratic equation. You use the quadratic formula, negative b plus or minus square root of b squared minus 4ac and all that. So, quadratic formula, and it simplifies to just this. So you see, when the detuning is 0, of course, this just reduces to plus or minus omega 1 over 2 as we expected. That's just going to be the Rabi frequency. But otherwise, it's going to be more complicated, right? We can define this as delta plus or minus an omega over 2, where omega is this quantity right here. We're going to call this detuning is sort of geometric or whatever average where is the geometric? Well, whatever. It's the quadrature, I guess, addition of omega 1, the Rabi frequency, and the detuning. So this is what we call omega without a plus or minus. So that's what we have. And then, of course, those are your solutions. So we can just write down what gamma up and gamma down are as a function of t. And of course, we know that these are the two fundamental solutions, right? So we have to choose the right combination of them to match the initial condition. And our initial condition is just that it's at t equals 0, you have the thing pointing up. So it means at t equals 0, you have to have gamma up is equal to 1 and gamma down is equal to 0. So the linear combinations of that, well, this one is, and we also need a normalization, of course, that these add up to 1. So what you get is the following. You get I omega 1 over this guy minus I delta t over 2. That comes from this delta over 2 business, but then you pick the combinations of plus or minus, right? They give you a sign. Yeah, so you get a sign. Someone's got a speaker on or something. So you get a sign omega t over 2. So that ensures that's the combination of exponentials, right? That ensures you get that gamma down is 0 at time t equals 0. And over here we get e to the I delta t over 2 over omega. And here we get omega cosine omega t over 2 minus I delta sine delta t over 2. So I didn't, you'll practice working out this kind of thing on the homework, but this is just what you end up getting when you solve this differential equation for the gammas. And these are just the combinations of these exponential solutions that ensure that you satisfy the initial conditions and so on. But it's just a solution to this differential equation right here. Given this as an initial condition. Yeah, and also, of course, it's normalized. So it looks a little funny, but it's actually not too bad, because we can look at, say, this down coefficient. You see now it's no longer proportional. So what did we have before? If delta is equal to 0, right, then this omega just reduces to little omega 1. It just reduces to the Rabi frequency, and then you just get a division here, omega 1 over omega 1. This just becomes 1. So what we get here is now a suppression of this amplitude by a factor of the Rabi frequency divided by this big omega, which is, again, this square root of omega 1 squared plus the detuning squared. So so that's what happens. Again, just to remind you what we had before. This time we wrote out the solution in this kind of funny way, but it was the same thing. The gamma down ended up being I sine theta over 2, where theta was omega 1 t over 2. With this initial condition where a is equal to 1 and b is equal to 0. Well, it's quite similar to the solution when we have this term being non-zero, except that, instead of this coefficient being 1, now it's suppressed by a factor of omega 1 over big omega. So that means that p down arrow as a function of t, if we take the magnitude of this guy squared, well, it's going to be omega 1 squared over omega 1 squared plus the detuning squared. This guy is just a phase that doesn't change anything. And this is sine squared. Here we'll just leave in the omega, because the point is this amplitude, right? The amplitude is now suppressed. It's smaller than 1. And it's suppressed by the detuning, right? And so now if I plot, say, p down arrow as a function of t, you still get the Rabi oscillations, right? But they're suppressed. Instead of going from 0 to 1, this probability only goes up to this factor of omega 1 squared over omega 1 squared plus the detuning squared. And then it oscillates. And the frequency of the oscillation is this omega, which is, again, the addition of omega 1 squared and the detuning squared. And remember what the detuning is. The detuning is the difference between the applied frequency and the Larmor frequency. So there you go. Those are Rabi oscillations. So the idea is you get a smaller effect. And of course, the P up arrow, of course, will go in sync with this. It'll just, they have to add up to 1. P down plus P up equal to 1. So it's just 1 minus this function. So you'll get oscillations, but they're smaller. You won't be able to flip the spin all the way down from the up direction, right? You'll be able to flip it a little bit. It'll go down a little bit, essentially. But of course, in quantum mechanics, that means there'll be just some probability of observing it in the down direction. But that probability will be smaller, right, than what you would get if you're on resonance and you're able to get the sort of maximum effect. And that's the physics of NMR. You can read in the Bellac book what happens in the actual device, how you can use this to do spectroscopy and stuff. I think that's a little bit too far afield. It's a little too applied for us. I just wanted to show you that you can sort of use your knowledge of, just the time-dependent Schrodinger equation to understand this seemingly complicated problem, but it's not too bad, especially for a spin 1/2 particle, because it's just a qubit. So everything he just reduces to a system of differential equations. So at most you have to bust open your differential equation book and remember how second order ordinary differential equations work. But that's, in terms of the math, that's kind of it. And in terms of the physics concepts, it's just a qubit for this particular time-dependent Hamiltonian. I forget if I erased it at this point. That's sort of what we start. Yeah, I have it right here. So in terms of the Schrodinger equation, it just means that you have a system of first order equations, which you then reduce to two decoupled second order equations for the two coefficients of your qubit. And that's also actually typically in most differential equations classes, you will have seen this. Maybe you forgot, but typically you would have seen how to solve something like this. That system of set first order differential equations like that. You probably have seen it, and how you can convert it to a set of decoupled second order equations. That's all we're doing. But I don't really want to. I showed you how to do it in the case of on resonance, and you'll practice some more of this kind of thing on the homework. But I don't want to dwell too much on it because we kind of have to move on to perturbation theory and variational method and stuff. But yeah, any questions about that? The physics is quite interesting, right? It's fun to think about just how the things we know correspond to these relatively complicated equations. Remember, we interpreted the on resonance solution as if it's a rotation operator applied to your initial state, right? And the rotation operator is along the x direction, which is that applied field direction in the rotating frame. And it's fun to think about off resonance. What does it mean? Well, in the rotating frame, what it would mean is that if you're not on resonance, then your applied field in that rotating frame is still rotating. So it's not going to have as dramatic of an effect as if it were a static field, because you're in a sense going to average over that rotation, and it'll be as if, you know, the field is weaker in a sense, and so that leads to this suppression, right, of the probability by the detuning. So sort of, it's important to try to connect these solutions, which we can do by, you know, applying what we know about differential equations to what's going on physically. So try to visualize in your head what happens if you, again, this is the basic picture, right? You have a spin pointing in some direction, and then you have a static field here. And so it'll process around the static field. And so then you just think about what happens if this rotating applied field, what if I just rotate it with the spin, right? That's the co-moving frame. And then you can either be on resonance, where it's exactly matching, or if it's off a little bit, then it'll rotate a little bit faster, a little bit slower. So the field and the spin will be out of sync. And so if you average over that, that'll lead to an overall suppression of this Rabi frequency spin flipping. But the Rabi frequency spin flipping is itself a kind of precession, just in a rotating frame. So that's, all right, hopefully I sort of beat that to death, but it's important conceptually, because the formulas are relatively complicated, I guess. All right, any questions before I move on? Actually, I'm going to clear all this now. Maybe it's a little more convenient to rewrite this quadratic equation if we multiply through by omega 1 over 2. This becomes, right, it's a little bit easier to see the quadratic equation solution than maybe if we put plus sign, let's see, a minus sign, Quadratic formula, right? Negative b would be delta plus or minus square root of b squared, which is delta squared, minus 4ac. So minus 4 cancels this 4. A is 1 and c is omega 1 squared. So that's this guy over 2a, which is 2. All right. So it's a little easier to see it this way. But anyway, yeah. All right. I'm clearing now. Hopefully that all makes sense. And so now you should be ready to practice it on the homework. Okay. So now we're going to do something a little more general. We looked at different applications. We looked at the hydrogen atom and spherically symmetric potentials. That was kind of application of the stuff we did in the last part of the class, the angular momentum. Then we looked at bonding, which is an application of the first part of the class where we looked at just finite dimensional Hilbert spaces and doing kind of eigenvalues and eigenvectors for matrices in order to find the energies and the eigenstates and so on. And then this last bit with NMR was an application of the time-dependent Schrodinger equation, which in this case we can solve exactly. And so what happens, and all of these things are exact solutions. You know, they might be simplified models. Well, hydrogen is really just an exact solution for the Coulomb potential. We had that funny model for molecular bonding. But what happens if you have a Hamiltonian, right, that's very complicated and you don't know how to find its eigenvalues and eigenvectors? What if it's just too complicated? You can't solve it. You can't solve the Schrodinger equation in any representation. If maybe the differential equation, associated with the Schrodinger equation is too complicated to solve. It's got too many coefficients in it that vary maybe. So then you have to use some kind of approximation, right? And so that brings us to just the general theme of approximation methods. And there's a bunch of them. Of course, we will consider three main ones, which is the variational method, which I'll do first. Then we'll talk about perturbation theory. And then we'll talk about the WKB approximation. You've probably seen the first two and haven't seen the third. They're all based on different ideas. So, but they're all related in the sense that we're just trying to, again, solve the Schrodinger equation. Well, for these, we'll be looking at the time-independent ones, just the eigenvalues and eigenvectors of the Hamiltonian operator. We're trying to solve for those in an approximate way. So variational method is based on the idea that you can construct a bound for the lowest energy eigenstate. So this variational method is typically used to approximate the ground state, the smallest eigenvalue. That's the way I like to phrase it, because so smallest eigenvalue of your Hamiltonian. And what's the idea is, remember that if you have any Hamiltonian, even if it's horribly complicated, and you find its eigenstates, phi n, abstractly, maybe we can't actually do it, but it doesn't matter, then we know that any state in our Hilbert space, we can decompose into some linear combination of the eigenstates of H. This is just a property of the Hilbert spaces, right? It's the spectral decomposition theorem that, the spectrum of H, its set of eigenstates, will span your Hilbert space. So you can write any vector in your Hilbert space as a linear combination. And there's another condition that we know H acting on this we'll call this the ground state. This is the eigenvector corresponding to the smallest eigenvalue. This will have, some eigenvalue, E naught, that's sort of the smallest. This is smallest eigenvalue. So what can we do? We can consider the following expectation value. We can take any state and construct its expectation value with H. And we can compare that to the expectation value we would get if we sandwiched the Hamiltonian between the ground state. So what do? We take this phi, we plug in this expansion. What do we get? Of course, we get the double sum, Cm star, Cn, just from the expansions of the bras and the kets. So you get this Hamiltonian. I'm gonna say the phi n is a little bit annoying. Let's not call it phi n, but let's just put n. It's a little more convenient. Just label it with the eigenvalue, the eigenvalue index. So you get that for the expansion minus E0. Then what? Well, we know that these guys are eigenvalues or eigenvectors of H. So H as a matrix is diagonal in those. So this has to be sum over n. The only terms that contribute are the diagonal ones, and you just get the eigenvalue, right? And then we can also do a little trick, right? And we can stick in a factor of 1 because this state is normalized, so this is just equal to 1. We can do a little trick and stick in a 1 there in front of the E0, and so this becomes sum over n, Cn squared, En minus E0. Oh, so again, H acting on any of these n's will give me some En. And right, this is a small, and these are the rest of the eigenvalues. And we know this is the smallest one, so this whole thing must be greater than or equal to 0. And that's the principle of the variational method. This is really the only thing you ever need to remember about it. This is the physics of it, is that the expectation value of the Hamiltonian with respect to any state whatsoever is always going to be greater than or equal to the expectation value of the Hamiltonian with respect to the true ground state. And of course, we can construct any state, so we have this at our disposal. And we need this because remember, a variational method is designed to find the ground state or approximate it. So we have an arbitrary state and we want it to get as close as possible to the ground state. And the idea here is that we can use this inequality, right? If we somehow make this expectation value here as small as possible, then hopefully we can get it small enough that we basically saturate this inequality, meaning that we get as close as possible to this guy. Because this will never be smaller than this. So if you can get it smaller and smaller by choosing an appropriate, like a better and better arbitrary state, then, maybe we can do a good job, right? So that's what you do. You use your imagination to construct some arbitrary phi that'll be a function of some parameter. Or maybe a set of parameters if you're really ambitious. It's some parameter you can vary, right? And then what you do is you calculate this expectation value, and hopefully this expectation value is sort of easy to calculate. It typically is, right? It's typically just taking some integrals, because even if H is complicated, expectation values of it are usually easy to calculate because it's just some set of derivative operators with some coefficients. So you just end up doing some integrals, and you pick a simple enough trial function where you can do the integrals. But you pick one that's as a function of some parameter alpha, and then you just say, well, I want to minimize this. So I calculate this expectation value, and let me just call this something like, average of H as a function of alpha. And we know this thing is always going to be greater than or equal to the true ground state. So what you do is you just try to minimize over alpha. And you remember that if you minimize, of course, then the derivative with respect to alpha has to vanish. Would be a local minimum, local minimum or maximum, of course, you have to make sure that you're actually finding a minimum, but you can find the local minimum. Or let's just say, you want to find the minimum, of course. And so remember, that's just the first derivative test. You look for where the first derivative vanishes. Those are your critical points. And, you find the one that corresponds to the minimum of the expectation value as a function of this parameter. Of course, if you remember your Calc 3, then you know that you can also have H be a function of a bunch of parameters if you wanted, alpha 1, alpha 2, and so on, however many you want. And then there's the equivalent of the first derivative test, which is that the partial derivatives with respect to any of the parameters, that they all vanish simultaneously. That's if you're in a multi-dimensional space, right, and you had one of these minima, then you're kind of in a little well, a multi-dimensional well, and then at the bottom of it, all the derivatives vanish in all the directions, so along all the parameter directions. So this you'd have to just make sure the derivatives vanish for all parameters I. So, but you can do that. You do the first derivative test, and then you just make sure it's a minimum, and then you plug in that value of alpha, right? And then if you plug in that, you find that minimum value, we call alpha star, or if you have a bunch of parameters, then it's that value. It's just a solution to this equation. And then you substitute it back in, and then you say that, well, fine, then whatever it is at alpha star, this expectation value must be a pretty good approximation to the true ground state energy. And, phi alpha star, the state itself, must be a pretty good approximation to the ground state. That's the idea. Sometimes, if you're really lucky, you might even get it exactly right? If you pick just the right trial function that has the right shape, sometimes you can get it exactly right. But those are typically nice coincidences. And so all of the art of the variational method is in picking a nice enough trial wave function where it's simple enough to calculate, but also complicated enough that it sort of captures enough of the features of the true ground state for it to be reasonable. So now we'll do an example of this. But yeah, any questions about the kind of overall scheme?
So alpha star is the value for which the expectation of the Hamiltonian is minimized?
Yes, I can put, yes. It's when alpha is equal to alpha star, that's when the derivative vanishes and you're at a minimum. That's right.
How do we know that we're at minimum?
Well, it's like anything with the first derivative tests, you'd have to check in principle. Usually the function is simple enough that there's just a single critical point. You don't know for sure. You'd have to do the second derivative test, right?
Right.
But
Okay.
usually you don't want to do that because it's too complicated. Usually you just find one solution to the first derivative test, and then you're like, well, it's probably the minimum.
Okay. So okay.
Well, if you're finding multiple solutions at this stage, well, probably your trial wave function is not very good.
I mean, when you have more than one parameters like alpha 1, alpha 2, and so on, maybe for alpha 1 and alpha 2, I find the minimum. What if alpha 3 is not the minimum? That's my original question.
Oh, well, then that would be a saddle point. You don't want that one.
Okay.
You really want to find a true minimum, right? In a multi-dimensional case, yeah, you're right. You might find something that's sort of a minimum in one direction, but a maximum in other directions, so you might get a saddle.
Okay.
So that you don't want that, because that means there are states which do better, right, for this expectation value, which minimize it more. So you don't want that. Sometimes maybe your trial wave functions is such that the minimum occurs for a boundary value of alpha. Maybe you have your parameter only make sense if it ranges from like 0 to infinity. And maybe for your trial wave function, the minimum is like for the parameter going off to infinity. There's cases like, in fact, the variational method is powerful for that reason. Sometimes you don't find a minimum in the sense that your parameter runs away to some value where maybe your trial wave function essentially vanishes. You can get stuff like that, and that actually leads to this interesting method of proving that states either have or don't have a ground state. So imagine your Hamiltonian is just a funny one that doesn't have a ground state, right? It's possible. It's certainly very feasible that you just don't have any bound states at all. And in that case, your variational method will start messing up. And that's a cool way of actually proving that, or at least getting a hint that you have or don't have a bound state, right? So that leads to some interesting problems, or it's an interesting application of the variational method, actually, is to see when it fails. Actually, I can tell you that you don't have a bound state. But okay, well, we're gonna yeah, any more questions? That was a good one.
So I was just wondering if you knew of any programs that could like quickly do this if you gave it a trial wave function, not to do the homework, but just in general.
Yeah, that's a good question too. I mean, there's certainly, you can numerically, once you have, so the hard part actually is generating this function. Once you have this function though, you can use numerical methods. There's like Newton's method to minimize and find like the best value of alpha. But in general, I mean, the computationally kind of tricky part is calculating this expectation value. But it's like taking integrals. So I don't know. I mean, so once you have a function, though, you can use like any find minimum function, right? You can use any find minimum routine in almost any kind of software package that does mathematical, numerical stuff, right? There's always some kind of minimization routine in like MATLAB, Mathematica. There's, Levenberg, Marquardt method or whatever for just numerical minimization as a function of any number of parameters. If you've ever done like fits to data, right? You minimize sort of at least so some of the squares of the residuals between your data and your fit function, right? That's a minimization thing. So you can use any of those routines to do this. It's just, there's no general way I can tell you that for calculating this, right? Because that'll depend on the Hamiltonian and the trial wave function that you're using. So I don't have but once you have that, then yeah, sure, you can use any numerical method you want for minimization. Okay, so that's good too. So any more questions?
Just one more.
Great.
There is a minimum. There's some optimal value of alpha. So it's like alpha star 1 or alpha star 2 or one of those values that's going to give you an approximation or close to the ground state energy, right? That's or what do you mean by for all I?
Oh, right. So
It needs to be
Let-
0.
let's do an example of 2 dimensions, or you have an alpha 1 and an alpha 2. What your and so now this is your function. The expectation value is a function of alpha 1 and alpha 2. A local minimum will look like, a well, right? It'll look like
Mhm.
a parabola like this, or paraboloid.
I
Hopefully
follow.
it's like a cup, right? And then
Yeah.
this will correspond to some unique point, the bottom of it, right? The bottom of this cup, it'll
Mhm.
correspond to a unique alpha 2 star and a unique alpha 1 star. So there's a special value for a fixed alpha 1 and alpha 2 for which you're at this bottom of the cup. And at that bottom, all the partial derivatives vanish.
Okay.
The
I
h
follow.
along the alpha 1 directions vanishes, and this along the alpha 2 direction, it vanishes. And that only occurs when alpha 1 is equal to alpha 1 star and alpha 2 is equal to alpha 2 star. That's all I'm saying.
Okay. Okay. Got it.
Nice. Okay. If you want, I could have written it. Maybe it's more convenient to just say the gradient in alpha vanishes. Maybe that's simpler to. Yeah, I agree. It's a little bit confusing. But this is
Yeah.
you just have to.
Yeah. There is a value of alpha, whatever dimensions you're considering, for which you have the lowest E0 or
Yeah.
some approximation. Okay, got it. Cool. Thank you. And in response to the previous question, there is one of the algorithms, the quantum classical algorithm, the variational quantum eigensolver. Have you heard of that, Max? I don't know.
No, I haven't heard of that. That sounds interesting.
That is where you find the ground state of this. You put in an input Hamiltonian function and you get a ground state from the quantum computer, and then you feed that into the alpha that you get from that. You feed that into a classical optimization routine. And then you do that multiple times to get the lowest alpha, or the optimal alpha for which you have the lowest energy. So at least there's one that I'm familiar with that does this.
Oh, that's cool. But I guess you still have to feed it in the expectation value. Probably.
Yes. So it kind of splits the Hamiltonian into different pieces, and then it calculates the expectation value for each piece. But it's the whole algorithm does it. It's supposed to do it for you, both the quantum part and then the classical part is part of the.
What's it called? I'll just write it down in case
It's
people want
the
to look it up.
VQE, variational quantum eigensolver, for anybody who's interested.
Sorry, what was the thing?
Variational.
Quantum, was it called quantum classical?
It is a quantum classical algorithm,
Uh,
and it's called a variational quantum eigensolver.
oh, okay. Okay, that's cool. Yeah, I'll have to look that up myself. I'm not familiar with it.
Yeah.
Guys, yeah, remember I'm a biophysicist.
No, yeah, that's totally fine. I just thought that, because there was a question of whether there was a program that would do it. I just wanted to say there's at least one, and they do consider other variational methods for quantum computing as well. There's a review paper out and so on and so forth. So I'm just doing stuff related to this right now, and this is directly applicable.
Awesome.
Yeah, thank you.
Yeah, well, thanks. That was good. I'm glad we're getting some some feedback. This is great. All right. So, anything else? Yeah. So let's do an example. I guess this is. I believe I originally got this from Sakurai, but the example is just a. Well, see, it's funny with these examples. If you ever read, you read these quantum books, whenever they talk about approximation methods, right? the example they give you is always one which is exactly solvable anyway. I always thought this was bizarre. And I get it. Like once you're done with the example, you can compare it to the exact solution and be like, oh, look, our variational method worked really nicely because we got close to the exact solution. But it's like a complete waste of time because you already know the exact solution. It's just, I mean, if I were to ever write a quantum book, I would probably try to think of an example where like there's just impossible to get an exact solution. So then when you actually do this, you feel like you've actually accomplished something. But you know, what can you do? We have to use the examples that are given to us, I guess. But maybe someday I'll think of a good example where you don't have an exact solution anyway. But yeah, so we're gonna do the infinite well where, you know, it's just infinite well, near potential, hard walls, so just vanishes outside of some interval. It's infinite outside of this interval and is zero otherwise. And we know what the exact solution is. The wave function for, you know, the zero state is just the cosine. There's a normalization, but it's just the single kind of, it's just the cosine, right? The ground state is a little hump there that's given by the cosine. So we know everything about it and we know what the ground state is and so on, but let's just do this futile thing, or, you know, waste of time thing where we apply the variational method. So when you apply the variational method, you want to put in as much information as you have. So in this case, you know your potential blows up here. So at the very least, you would want your trial wave function to vanish at the boundary there. So you'd want it to, and this is at, you know, minus a and plus a. So you want it to vanish there. So let's try the following wave function for a trial wave function. Let's just try a normal. So you're gonna have to normalize it, but let's try the following. Let's try a raised to the alpha power minus absolute value of x raised to the alpha power, and alpha is our parameter. And this thing, you know, it kind of, if you're making a hump, it kind of changes the shape of the hump, right, depending on alpha. As if alpha is 2, you get like a parabola shape. If alpha is 1, then you get like a little cuspy linear shape, and you're kind of changing that curvature of your hump, right? As you make alpha smaller, it just becomes kind of cuspier. We make alpha bigger, it becomes more kind of rounded. So it just changes the shape of the hump, and we're just going to try that as a trial wave function. Of course, we know the real solution is a cosine, and if you think about, you know, Taylor series expanding a cosine, it's got like a kind of parabola-like shape around x equal to 0, around the tip, you know, this thing, you know, around 0, it'll kind of look parabola-ish, because the cosine has that Taylor series 1, and the next term is an x squared. Okay, but so that's the idea. But why did we choose this wave function? I don't know, just because to try it for fun. And the other important point is that this vanishes when x is plus or minus a. So it incorporates the boundary condition. That's an important aspect of this, is that well, you want it to incorporate as much information as you have, and the information you have is a thing blows up, and so there you would want your wave function to vanish. So the first things first, what you would normally do, sometimes you don't do this, but often it's nice to normalize it right away. So you just get the trial wave function. You don't have to. You see, your trial wave function, actually, I didn't emphasize this, but this expression here, it's sort of independent of whether or not you normalize phi or not. So sometimes it's convenient to actually not normalize it. And then, of course, you have to go back to what I did there. It's a little bit subtle, but you have to go back to this thing, and then you can actually put back in. This is just a normalization of your wave function. This is typically 1, but it doesn't have to be. Sometimes you don't normalize. Anyway, it's just a little aside, but sometimes in the variational method, you don't have to normalize, and then the normalization just comes along for the ride. But that's an aside. We are going to normalize for now. So, or in all these examples, so we're normalizing. So that's the first thing you would do is you normalize this. So what do you want? You want that the twice n squared times the integral from 0, because it's a symmetric function around the origin. So you want twice the integral from 0 to a. And now we can drop the absolute values, just a raised to the alpha power minus x alpha squared dx. We just have to make sure that that's equal to 1. Guess I'm running low on time a little bit, but you can, this is just, you multiply this out, right? You get a bunch of, you just get 3 terms, and fine. We can do it out, I guess. So you get 3 terms. The first one, a raised to the 2 alpha. This just becomes a. It's just the integral of x. Then you get a minus 2 a to the alpha. You get a to the alpha plus 1 over alpha plus 1. That comes from the cross term. That's just the integral of x raised to the alpha power. And then you get the other, the last term, which is x to alpha squared, so it's 2 alpha. So it's 2 alpha plus 1 over 2 alpha plus 1. And that actually simplifies to 2n squared, 2 alpha squared over alpha plus 1. You can just do a common denominator thing. And then this whole thing is multiplied by a to the 2 alpha plus 1. And that's equal to 1. And so you can solve for the normalization constant. And this is, since we're out of time, but I'll finish here, is just that this is your trial wave function now with properly normalized is the following: alpha plus 1, 2 alpha plus 1 over 4 alpha squared. So just solving for n, substituting in for n, and then it's absolute value of a raised to the alpha minus absolute value of x raised to the alpha. So you see the trial wave function is incredibly, it's just kind of ugly. And unfortunately, that's just the way it is when after you normalize. And now we're going to use this and calculate the expectation value of the Hamiltonian with respect to this, complicated trial wave function. But as you'll see, it's not so bad when you do that. So next time I'll do that and show you what kind of result you get. And unsurprisingly, the minimum of the alpha star that you get will be kind of close to 2-ish. That's sort of what we'd expect, because the real solution is a cosine. So it's kind of parabola-ish. And the optimal value for alpha, you'll see, will be close to 2, and we'll actually get pretty close to the true ground state energy. Before you go, I'll just mention that, of course, this is the exact solution, and the exact ground state is h bar squared pi squared over 8m a squared. That's the exact stuff. And then we're just going to compare our variational method solution to this exact one. But yeah, that's next time. All right, any more questions? All right, let's see.